Hello there. My name is Mohammed. I'm from the University of Glasgow. It's a pleasure to be here today to present GazeWheels, comparing dwell time feedback and methods for gaze input. GazeWheels is a set of methods for visual feedback and input using eye gaze. This is how it looks like. The idea is to provide the user with visual feedback in the form of a wheel that gradually gets filled as the user looks at the target. When the wheel is completely filled, the selection is made where the user is gazing. So interacting using eye gaze is very promising. Gaze is generally fast. It's, for example, faster to gaze at something rather than to point at it with your mouse pointer. It's also natural to use, so people usually know how to catch up how to use it really quickly. But a challenge in gaze interfaces is that the system needs to distinguish whether you're looking at a target to select it or if you're looking at it to perceive it. So it has to distinguish interaction and perception. And this is a problem known as the Midas touch problem. There has been solutions proposed to the Midas touch problem. The first of which, or the earliest ones by Rob Jacob, was actually dwell time. So dwell time refers to the idea of selecting a button, for example, only after you've gazed at it for a few milliseconds. So for example, for half a second. So this way the system is able to distinguish whether you're just perceiving the target or if you actually want to select it, depending on how long you look at it. Another option is to use multimodal interaction, so to combine gaze with another modality. For example, you look at a button and then you press the space bar on your keyboard to select it. Or in case of a mobile phone, you look at a target and then you press anywhere in the touchscreen to do it. And there has been also other techniques that were proposed that rely on gaze behavior for input. So behaviors such as gaze gestures or pursuits. So for example, pursuits is about the idea in pursuits is to show the user moving targets, and by comparing the movements of the eyes, you can tell which target the user is looking at. And this concept or this approach is actually robust against the Midas touch problem. Gestures, on the other hand, they are when you perform a coarse eye movement with your gaze, so moving from one point to the other to perform a gesture to the right or to the left, similar to touch gestures on the phones, but using eye gaze. Despite the recent approaches that are robust against the Midas touch problem, dwell time still remains to be relevant, because unlike pursuits and gestures, dwell time can actually replace your mouse pointer, or in case of touch screens, it can replace tapping. And this form of interaction, like tapping or selecting with the mouse pointer, it's a form of interaction that everyone is familiar with. Also, unlike multimodal interaction, dwell time does not require any additional hardware such as a keyboard or a touchscreen. So our proposed gaze wheel aims to provide the user with feedback in different forms when providing input using dwell time. We implemented multiple variations of gaze wheel. The first one is here on the left. What happens here is that when the user gazes at a target, a wheel appears and starts getting filled as long as you are looking at the target. Now, if you look away from the target, it resets, and hence the name Resetting GazeWheel. In the second variation, looking away from the target doesn't cause it to reset, but actually causes it to pause, and then it resumes again when you look at any other target. So as a result, this makes the interaction a bit faster. And in the third variation, the wheel is always getting filled, and a selection is made only if the wheel is filled while the user is gazing at the target. And hence we call it Infinite GazeWheel, because the wheel keeps on filling regardless of whether you're looking at the target or not. In addition to the three implementations of GazeWheels, we also experimented with the location of the feedback. So the feedback could be co-located as here on the right, so it appears on the button, or it could be remote as on the left, where it appears above the keypad. We also tried different dwell durations. We tried 500, 800, and 1000 milliseconds, or 1 second. And these values were chosen based on previous work. So these were the values that performed well in previous work. After implementing GazeWheels, we evaluated it in a user study. So we recruited 19 participants, 10 females and 9 males with normal or corrected to normal eyesight. And then we followed a within subjects design where we had two independent variables. The first was the method of GazeWheels, so whether it's a resetting, pause and resume, or an infinite GazeWheel. And the second independent variable was the location of the feedback, so whether it's remote which appears above the keypad or co-located on the target itself. And then in the study setup, we used Toby4C eye tracker, and we asked participants to provide input on an on-screen keypad, assuming the user is entering a pin on an on-screen keypad. The procedure was as follows. First, the experimenter explained the different methods, and then participants underwent a training phase. The participants were then provided with a sheet of random pins to enter, and they entered 9 pins using each of the 6 conditions that I explained in the previous slide. Each 3 pins were using one of the studied dwell durations, either 500, 800, or 1000 milliseconds. In total, we collected 1026 entries, and we measured entry time and error rate for each of them. And then we concluded with an interview to collect qualitative feedback. Now let's take a look at the results. The graph shows the entry times using the different methods and different dwell times, and these entry times actually include the time taken to correct any errors. So let's say, for example, you enter a 4-digit PIN. The last digit that you enter is incorrect, so you had to delete it, and then you had to enter a new one. Actually, the shown entry times here include all of that time. And interestingly, we see here that when using low dwell durations, such as 500 or 800 milliseconds, the differences in entry times among the different methods are actually negligible. So even when factoring the time taken to correct errors, the differences are negligible because, as we'll see next, the pause and resume and the infinite methods are actually they have more people do more errors when using them. So, but nevertheless, even when including the time taken to correct errors, overall, people take the same time when using the different methods. But then when we exclude the time it takes to correct errors, we'll find that the infinite and the pause and resume GazeWheel variations are significantly faster than the resetting GazeWheel, which we actually treat as a baseline because this is the default implementation of most systems that use dwell time for gaze input. And then when looking at the error rates, we find that they are significantly higher when using the pause and resume and the infinite GazeWheel compared to the baseline, which is resetting GazeWheel. So to summarize the results, although infinite GazeWheel and pause and resume GazeWheel elicit more errors, completion time vary only slightly when including error correction time. So while of course low error tolerance can be frustrating for many users, we expect that actually learning effects would make people faster over time if they use the infinite and the pause and resume method for a long period. We found no significant influences of the feedback location, so we didn't find significant differences in entry time or in error rates when showing the feedback on the buttons or away from the buttons. Finally, I also mentioned earlier that we interviewed participants at the end of the study, so the detailed qualitative results are in the paper, but we generally got very mixed feedback. So some people loved the methods, especially the infinite and the pause and resume one, and others actually hated them and preferred the baseline, which is the resetting GazeWheel one. From this, we learned that probably it's good to keep in mind that they are not suitable for everyone and that people should have different options to choose from. For future work, we want to experiment with using different types of feedback, including vibrotactile and auditory feedback. So actually, there is a lot of research about using these feedback modalities for gaze interfaces, but we want to combine them with the concept of GazeWheel. So imagine if you can feel tactile feedback on your hand that goes in the form of a wheel, where if the wheel is completed, then a selection would happen. And we want to also evaluate GazeWheel in interfaces beyond keypads. So we chose pin pads because there is a growing importance and relevance of eye tracking in security applications. But of course, there are many other applications beyond that which would be interesting to experiment in. Thank you very much for your attention. This work was partially funded by the Royal Society of Edinburgh and also by the joint scholarship between the University of Glasgow and University of Edinburgh, which funds my PhD student. Thank you for your attention, and here are my contact details if you want to get in touch.